Thank you for introduction, Chairperson. I'm Yusuke Ishii from Chuo University in Japan. I will make a presentation on this title. First of all, wearable robots have been developed in industrial and medical industries, especially power skeletons that augment physical movement is expected. For example, augmentation on jumping movement allow rapid movement on an even terrain and overcome obstacles of 1 meter or higher. So, okay. So development of power skeleton that augment jumping motion is needed. Study on power skeleton that augment jumping motion includes exoskeleton with motor and exoskeleton with artificial muscle. The motor has low compliance and low output per weight. So human motion is inhibited by motor. And on the other hand, artificial muscle has high compliance and high output per weight. So human motion is efficiently augmented. But this study only increased height by a few 10 millimeter or less. This is small increase from without skeletons. Therefore, development of power skeleton capable of increased jumping height even more is expected. And so purpose of this study is to develop power skeletons that augment jumping motion by developing interactive phenomenon between power skeleton and human generated horse. However, there are issues in exoskeleton development. For example, difficulty in augmenting jumping motion due to actuator weight and difficulty in creating an environment due to the dangers of human experimentation. And so we use pneumatic artificial muscle with high compliance and high output per weight. And in addition, as first step, we use humanoid robot to simulate safety with actual equipment. And therefore, method aimed at increase jumping height in classified into A, parallel horse, and B, serial horse acting weight. But comparison of A and B has not been made clearly. So it can be used to develop a power skeleton. So first, we aim to construct a model of a human robot and power skeleton, and to compare the increased jumping height by the attachment method of the power skeleton through dynamics analysis. Next, I describe the jumping robot model based on human jumping mechanism. The jumping robot is loaded with weight assumed whole upper body and connected to the top and hood. And this jumping robot is driven by DC motor. And power skeleton is driven by pneumatics artificial muscle. And there are two attachment methods for the power skeleton: A, parallel attachment, and B, series attachment. In parallel attachment, power skeleton adds parallel torque and to the knee joint by rotation independent of knee. On the other hand, in series attachment, power skeletons are rotate independently on joint, and the upward force gained by the arm striking the ground is added serially. Next, I describe the dynamics models that we constructed. First, jumping rope model. Equation motion or jumping robot is equation 1. Each term represents from left to right the inertial term, the control sugar and Coriolis horse term, and the gravity term. And center of gravity sphere at takeoff is equation 3. It is decided by the impulse or ground reaction force received until takeoff. Next part skeleton model. In parallel attachment, torque acting on the knee is equation 5. This is decided to sum of the jumping rope torque and parallel skeleton torque. And in series attachment, equation of motion or parallel skeleton is equation 6. Each term represents left to right and the actual muscle turn, the ground reaction force turn, and the gravity turn. So firstly, model of motor and ground reaction force. DC motor has linear relationship between torque and speed. So output torque of motor is expressed by equation 7, and ground reaction force is expressed by equation 8 as hypothetical nonlinear viscous elastic model. So next, I describe dynamics analysis. Purpose of analysis is to estimate the jumping state from dynamics analysis and to compare the increase or jumping height by the attachment method of parallel skeletons. And in this analysis, a maximum jump height or the hip joint is compared. Analysis conditions. A jumping robot's hip is fixed to the guide rail, and constant voltage 24 volt is applied to the motor until takeoff. For parallel skeleton, we assume that contraction force or axial muscle has linear relationship with amount of contraction as equation 9. And parallel skeleton drive timing is in parallel attachment is the same timing as motor drive. In series attachment, it is 0.095 seconds after motor drive. Yes. Analysis result. Figure 15 shows jump height for the attachment method. From this result, jumping height is maximized in series attachment, and it is 1.18 times the jumping height without the exoskeleton. And figure 16 shows motor work for the attachment method. From this result, motor work is minimized in parallel attachment. So, and it is 7.1% decreased. And from this, we believe in parallel attachment, parallel skeleton has high assist role. So therefore, series attachment is expected to augment jumping motion. So finally, conclusion. In future work, we will reveal the effect of parallel skeleton drive timing on jump height, and we will confirm the validity of model. Thank you.
It's interesting work. I don't know if there are any questions. Please.
Thank you. You analyzed in your research take-off, but my question concerns the landing, because in landing we will expect the high impact. How you will dump this? Do you think that the springs, just the passive dumping will be sufficient, or you assume to develop the active dumping with the support of the motors? Can you a little bit elaborate this question?
Thank you. In this story, I didn't consider running. So, but I believe in series attachment, exoskeleton decrease impact because shear elastic and more artificial muscle. So I think in shear attachment is power skeleton can receive can reduce impact. Okay.
Some other questions? So I have one question. You said you did only this in simulation.
Yes.
Which simulator you used, or because if I understood correctly, you did this in simulation, and also you used a robot to make, and then you will also try when you have, for instance, one person, because the idea would be to put this in exoskeletons when mounted on human people. So my question goes to which simulator you have used it, and how have you dealt with difficulties like adding noise, and when you need you will use sensor information, if these have latencies or delays, and in which way this can affect the outcomes of your simulation, your model that you developed.
Firstly, I use a simulator on a simulation X, and we consider friction and motor delay, but I didn't consider artificial muscle delay. Okay. Oh yes, for simulator simulation X.
Okay. Thank you. Just for finalize, do you expect these experiments, and when you go to real experiment with humans, you already try to evaluate which difficulties you expect?
Yes. So, it is difficult and actual size, and but first thing on jumping road, by jumping road is my phenomenon is if you can understand phenomenon by jumping robot, we can achieve their their environment. Okay, so